Access to accurate depth information is important for a wide variety of oceanographic science applications. For example, it is crucial in the creation of 3D models. The search of creating 3D virtual environments has been increasing due to the convenience of observing an environment virtually without having to be physically in the location. Researchers are currently creating 3D interactive models of coral reefs to help preserve the visual integrity of the underwater environment and observe the reefs from a remote location. In order to accurately depict these models, depth information is needed. During a summer REU program, I worked alongside 3 other teammates to create a depth collecting prototype called a Depth Sensor Enclosed Application, or DC, which is an underwater depth sensing device for standalone time average measurements. This video shows an example of a 3D model that the lab we were working with had created from surveying a coral reef over several years. This allows researchers to monitor and study coral reef health and the effects of weather damage on coral reefs over time. To build these interactive environments, depth information is essential to accurately depict the structure and levels of the reef, but gathering this data is cumbersome and expensive. Currently, divers are manually measuring depth by using dive watches, but this method is inconsistent because of variable depth readings caused by changing wave heights and human errors. To gather the data, divers have to lower the measurement device to the same level as a coral reef and log the data. To combat these problems, we created DC. Our compact, low-cost device automatically captures depth and pressure underwater and displays the information every 20 seconds on a display module with high visibility. To use this device, the user places it on top of the area of study, in this case a coral reef, and leaves it there to measure and average the depth submersion reading while accounting for differing wave heights on the ocean surface. Additionally, we have integrated an SD data logging feature to provide researchers information for later observation. As the divers conduct their surveys using the large camera setups, they will be able to also place DC on top of the reef to capture the depth readings through a camera. DC presents a solution for accurate underwater depth sensing over time. With this in mind, this device can be used for other applications such as capturing depth on autonomous underwater robotics, as well as 3D mapping for other underwater environments. A display is needed to view the depth data in real time while divers swim back and forth to capture images of the device and data shown on the screen. As a result, the display must have little to no glare, and the information on the screen must be seen from different angles. Diving conditions at coral reef communities are relatively shallow and highly illuminated. As a result, the display module should display the depth information as clear as possible under different conditions to make sure that information can be retrieved from the images accurately. From testing different displays, we saw that numeric LEDs are not legible from a camera on highly illuminated days, and LCD displays become hard to read when viewing it at angles greater than 45 degrees. On the other hand, the e-ink display was able to be read at more extreme angles and had much better contrast. Because of this, we decided to use the ink display for DC. The code for the ink module is developed based on Arduino libraries. We programmed it to have a refresh rate of 20 seconds. In our design, we implemented a sleep mode to power off the display when not in use in order to preserve the ink display functionality and power. The average depth at coral reefs is 10 to 15 meters underwater. We need a device that can withstand up to 30 meters of pressure underwater for maximum waterproof protection. One of the requirements for this device was to make it durable and robust when taken into the field for testing. As a result, the first method for completing this requirement was epoxy putting. Through our research, we found that the ink display does not react well with heat during the process of epoxying. To eliminate the heat factor, we put the PCB into a scuba box to encapsulate it and make it waterproof while also making it easy to debug. By using a commercially available scuba box, which can be opened after being submerged, we still have access to the components after underwater testing. This greatly reduced the cost and complexity of the device since the data can be easily accessed and the battery can be charged by opening the box. The box that we use is rated to be waterproof for 3 times the expected depth the device will be used at, so leakage is not a problem. Price, power consumption, waterproof rating, and reliability were the most important factors for making design decisions. This figure shows the breadboard prototype layout and the components included in the hardware implementation of DC. The components labeled from 1 through 3 are used for power. We used a lithium-ion battery with a charger and voltage regulator. The STM32 microcontroller is then turned on using a reed switch as seen on number 4. At the top, an e-ink display module is used to display the depth readings in real time. For component 6, an SD card is used for data logging and inserted into a card adapter reader module. The 7th component is a pressure sensor, which is used to calculate depth measurements. We constructed and tested a prototype of our device in a pool using a scuba box encasement. The goal of the test was to check the durability, accuracy, and visibility of our product. The accuracy and visibility were tested in comparison to a diving watch. In terms of durability of our scuba box encasement, this test was successful as the device did not malfunction when submerged underwater and the depth was being displayed on the screen. Everything worked as expected: refresh rate, on and off switch, and depth value. The refresh rate of the ink display was consistently 3 seconds, with the data displayed on screen for 17 seconds. We tested DC by placing the device at 4.40 meters underwater and compared the values to a diving watch in order to test for accuracy as shown. The diving watches have a reported accuracy of 0.1 meters. When DC displayed 4.40 meters, the watches displayed 4.3 meters, but the watches do not go to the hundredths place, so we do not know if the watches truncate the depth values. To test visibility, underwater cameras provided by the lab we were collaborating with were used. This test was to mimic how divers would capture images of the device by swimming back and forth while performing a photomosaic survey. This underwater camera was used to take photos of the device from different angles to observe the glare and visibility of the display. When capturing values underwater, there was a drastic difference in viewing the depth, as it was easier to view the numbers on DC, as numbers were bigger and had more contrast in the display. In the future, we are continuing to test the scuba box prototype for accuracy, reliability, and durability. We will test how much pressure and depth the scuba box can take, as well as the depth sensor's accuracy in averaging the depth measurement. As far as durability, we will be testing the PCB within the scuba box to see if the components are secured when taken out into the field, such as in rough terrain. We will be replacing the breakout board and placing all the components directly on a smaller PCB for easier and cheaper mass production. We plan to implement a magnetometer for information about sense of direction when underwater. Once the prototype is robust, accurate, and has all the added implementations, we will be handing the final device to researchers to have it tested in the ocean. Thank you.